Hello everyone, welcome back to the channel. In today's video, we are going to understand the concept of saturated liquid vapor mixture and a very important property called dryness fraction. So let's start our discussion with this TV diagram where from point 1 to point 2, the water is being heated at a constant pressure. So condition 2 represents a saturated liquid condition. A saturated liquid is a liquid that is about to vaporize. This means at point 2 the saturated liquid is ready to change its phase into vapor. Let's say we add some heat to this saturated liquid which is at point 2. So that will start the phase change process from liquid to vapor. So from point 2 to 3, the liquid is getting converted into vapor. And at point 3, that liquid becomes 100% vapor. So point 3 represents 100% vapor condition. So from point 2 to 3, it is a phase change process from liquid to vapor, and point 3 represents 100% vapor, which is also called as saturated vapor. Saturated vapor is a vapor that is about to condense. This means at point 3 this saturated vapor is ready to change its phase into liquid. So for saturated vapor, it is ready to change its phase into liquid. Its temperature and pressure is saturation temperature and saturation pressure. So for point 2 or for point 3 or for any point between 2 to 3, the temperature and pressure is always saturation temperature and saturation pressure. And this line 1, 2, 3, 4 represents a constant pressure line on the TV diagram. So this line here represents a saturated liquid line. That means any point on this line, any point on this line represents saturated liquid condition. This line here represents a saturated vapor line. That means any point on this line represents saturated vapor condition. Now this area between these two lines is represented as saturated liquid vapor mixture region. That means any point in between these two lines represents a saturated liquid vapor mixture condition. Now let's say we have a point A here between point 2 and 3. This point A represents a saturated liquid vapor mixture condition. In steam table, subscript small f is used to denote the properties of saturated liquid. Subscript small g is used to denote the properties of saturated vapor. The subscript small f small g denotes the difference between saturated vapor and saturated liquid. So now if I want to write specific volume of saturated liquid, I will write small vf. Specific volume of saturated vapor, I will write small vg. If I want to write the difference between specific volume of saturated vapor and specific volume of saturated liquid, I will write small vfg, which is the difference between vg minus vf. So condition 2 represents saturated liquid condition. So on a TV diagram, the volume corresponding to condition 2 represents specific volume of a saturated liquid, which is small vf. Condition 3 represents saturated vapor condition. Volume corresponding to this saturated vapor is called specific volume of saturated vapor, which is small Vg, and we already discussed Vg minus Vf is equal to Vfg. So we have this Vf and we have Vg. So Vg minus Vf is equal to this Vfg. Vfg. So Vg, this Vg minus this Vf represents this from here to here, it is Vfg. So Vg minus Vf is Vfg. I can also write from this Vg is equal to Vf plus Vfg. So this Vg is equal to this Vf plus this Vfg. So let's say if we have a point phi here, which is a saturated liquid vapor mixture, and if I want to calculate the specific volume of this saturated liquid vapor mixture at point phi, we need a new property called dryness fraction to calculate that specific volume at point phi. So the dryness fraction is represented by X. So the dryness fraction is the ratio of mass of vapor to the total mass of liquid vapor mixture. Mass of vapor is written as mg. Total mass of liquid plus vapor mixture is the mass of liquid plus the mass of vapor. So mf is the mass of liquid in saturated liquid vapor mixture. Mg is mass of vapor in saturated liquid vapor mixture, and m total is the total mass of saturated liquid vapor mixture. So let's say what will be the dryness fraction for point 2, which is a saturated liquid condition, which is a 100% liquid. So I will write X is equal to mass of vapor divided by total mass of mixture. So what is the mass of vapor at point 2? At point 2 there is no vapor because it is 100% liquid, saturated liquid condition. So mass of vapor is 0 divided by total mass. It will be mf plus mg. Mg is 0. So from this, dryness fraction at point 2 is equal to 0. So for any saturated liquid condition, the dryness fraction is always 0. So on this line, saturated liquid line, dryness fraction is always 0. So let's say for point 3, what is the dryness fraction? So point 3 is saturated vapor condition. That means it is 100% vapor. So I will write X is equal to mg divided by m total. Mass of vapor is present there because it is 100% vapor, mg. Total mass mf. Mf is mass of liquid. Is there any liquid at condition 3? There is no liquid because it is 100% vapor. So mass of liquid is 0 plus mass of vapor is mg. So that will be equal to mg divided by mg. That becomes 1. So dryness fraction at point 3 is equal to 1. So for any point on this saturated vapor line, for a saturated vapor condition, dryness fraction is always 1. So any point on saturated vapor line will represent dryness fraction of 1. So I can write like this. For this line here, dryness fraction is 0. And for this line here, dryness fraction is 1. So as discussed, for a saturated liquid line, dryness fraction is always equal to 0. For a saturated vapor line, dryness fraction is always equal to 1. So the dryness fraction changes from 0 to 1 between saturated liquid line and saturated vapor line. So let's say at point 2 it is 0, but from point 2 to point 3 it changes from x equal to 0 to x equal to 1. So these are the constant dryness fraction lines which is represented here. So these are the constant dryness fraction lines. So it is changing from 0 to 0.3 to 0.6 to 0.8, 0.9, and finally it becomes x equal to 1 at saturated vapor line.